Good afternoon, everyone. It is my absolute pleasure to welcome you all to this insightful hands-on session on ASIC design, that is analog IC design flow, a journey from schematic design to chip tapeout. In today's rapidly evolving semiconductor industry, analog IC design plays a crucial role in shaping the next generation of electronic devices. The entire design flow demands precision, expertise, and innovation. This session will provide a comprehensive hands-on experience, bridging the gap between theoretical knowledge and real-world applications. We are honored to have with us Dr. Saurabh Nath, who bring extensive experience in IC designing through this journey. Associate, Grade 2, in Ministry of Electronics and Information Technology, funded the prestigious to started Dr. Nath 2024, where he explored the design and analysis of analog front-end circuits for neurological disease detection. He also possesses an MTech degree in microelectronics and VLSI design from NIT Shilchar and a BTech degree in ECE from Sikkim Manipal Institute of Technology. An accomplished ASIC designer, Dr. Nath has successfully taped out 4 analog ASIC chips in the SCL 180 nanometer technology. His research focuses on developing innovative analog circuit designs for biomedical applications, driving advancements in healthcare technology. Dear audience, I encourage you to actively participate and ask questions and make the most of this opportunity to enhance your skills in this field. Without further ado, I would like to hand over this session to Dr. Nath. As Principal Sir is present, I would like to ask him to say a few words.
Am I audible? Am I audible?
Yes, sir.
Very good afternoon to all my dear students and dear Dr. Saurabh. Nice to have you with the head of the Department of Electronics and Communication and all my dear faculty members. It's the rarest of rarest occasions that we would have various personalities from either industry or academia many a times to share their experiences, their exposure, knowledge on the domain-specific topics, such as the topic has been chosen here, analog IC design flow. It's a very important portion for all of us to learn something from outside, because this adds a lot of value with the knowledge that we gain from inside from all the faculty members. Whenever we listen to the outside experts, this gives us a different flavor, add value to the skill, to the knowledge that we have. It's a good occasion. I hope that we all will learn a lot of things. My dear students, please be interactive and try to get more insights into the actual topic and the actual learning that we will be having. See that nowadays we are going through a rapid transformation, and we are stepping into the era of semiconductor design a lot in the coming days, and a lot of workforce is required in the semiconductor design in the days to come. Therefore, this is related to the semiconductor design to some extent. I would advise to all my students that you learn more in this aspect and become skillful so that you can get into the industry of semiconductor in a larger way. Wish you all the best, and congratulations to the entire department, Dr. Manoj Parai, Dr. Devojyoti Misra, and all the faculty members who are there, and all my dear students. Thank you very much for giving me this opportunity. Thank you.
Thank you, sir. Um, I would like to hand over to Dr. Nath. Please,
Yeah,
sir.
good afternoon, all. I am very much glad to have this opportunity to share my experience about the IC design flow and whatever I gathered knowledge in this division. And I am very much thankful to Mitun sir, my teacher actually, BTech, during my BTech, he is my teacher, and Manas sir for giving me such opportunity to share my experience. So actually, IC design flow has lots of steps. So in these 3 hours, yeah, I will be giving you a brief overview about how the steps or what are the things we need to take care of. So I will be showing you a small circuit, a CMOS inverter, and with that I will go for how the IC can be designed with using this CMOS inverter circuit. So I request all of you to be interactive and alert and have uh, attention in my presentation so that you can get some idea how the things are going on, what are the softwares and what are the tools we require to do these types of things. So let's start. So these are the outline, basic outline. Moore's law, I will be telling about Moore's law. Everyone knows about Moore's law. We'll say design style, ASIC design flow, front-end analysis and simulations, layout basics about how layout can be done, and then tape out process. Here, tape out means taping out means we are giving our design to some foundry, some fabrication lab. That's why we are using the word tape out. Another word is called tape in. In Intel, in Samsung, they actually do tape in because they have their own foundry files, own library files, own process kit. So that process is called tape in. So in our case, it will be a tape out process. We are giving our designs to some other foundry to fabricate it. So this is the Moore's law. I have shown some IC processors and the number of transistors rising. And the Moore's law states that in every 2 years the number of ICs will be doubled. Now it is also violating the rule. Now 18 months it is being doubled. So this is the race of rising transistor numbers in our today's chip. And another things I would like to share, that is the technology node. The technology node is the effective channel length of the MOSFET. So these are the technology nodes, yeah, day by day or year wise I have listed out here. And the technology node is calculated by the formula 1 by root 2 times of previous technology node. So this is the average formula, or you can say that you can think of. So now latest 5 nanometer, 3 nanometer, even beyond that is going on. So these are the technology node, effective channel length. Now let's come to the VLSI design style. So there are 3 main basic design style we have to follow during our IC design flow. One is full custom, another is semi-custom, and another is standard cell based design. Now, what is full custom? Full custom means if we have to design our MOSFET, everything by our own hand, but no, we will not be using the library files. We will be customizing our own cell during our design, which requires lots of time, and it is actually highly optimized. But due to the increasing number of transistors, full custom flows are not followed nowadays. Next is semi-custom based design. In this demo, I will be showing you the semi-custom based design. That is schematic driven layout. We will be to design our circuit in schematic level. That will be generated. That will be carry forward for layout using the foundry files. So this requires a moderate design time, and mostly mixed signal IC designs are done in using this semi-custom based design flow. Another is standard cell. So standard cell is the layout height. Layout height is fixed. Here the standard cell will be like that. Your height is fixed for certain foundry. It requires less design time, and very low coding and scripting based language is required for this type of design. IC design. Mostly digital IC designs are done using standard cell based design. Hope I am clear about up to this. These are the basic design styles. Now, what are the files required to do design a chip? Files or tools, whatever you can tell. So we require some tools, design automation tools. That is tools supported by Cadence, Synopsys, Siemens EDA tools. That's Mentor Graphics. Now it's the Siemens business. These are the three giant companies who are in the market for designing the chip or this type of flow, custom IC design flow. Another, we require a process design kit, PDK. This is actually a foundry library files given by certain company. There is UMC, United Microelectronics Corporation, and SCS Semiconductor Laboratory. There is, we are now, they are giving only 180 nanometer files. We have the access of 180 nanometer files. Next is TSMC, Taiwan based company. They have all the technology nodes up to 65, 45 nanometer is there, 7 nanometer is there. Another is Global Foundry and GPTK generic library by Cadence for testing. This is a generic library given by the Cadence itself to test the tool, nothing else. Fabrication is not, we will not be able to do the fabrication using GPTK. But a Global Foundry, TSMC, SCL 180 nanometer, the Foundry UMC, you can do fabrication. You can develop the IC. Now these are the two things we require to do the whole thing, whole process. Means we require a EDA tools, we are a foundry files, PDK file, process design kit file. So EDA tools we will be using here Cadence, and process design kit we will be using here SCL 180 nanometer technology. This is the Indian company, Chandigarh Mohali is the fab. Next, this is the IC analog IC design flow. Step by step, I will be explaining one by one how things are going on. So first, we will have some specification to design a analog circuit. We should have some specification about the circuit. Then we will do the schematic based design. Then we perform simulation to check the output, whether our specs are met or not. If not met, then again we have to change the schematic design. And if met, we will proceed for a layout design. And then we will do the layout verification, DRC, LBS specs. These are their design rule check, layout versus schematic, parasitic extractions. These are the steps, three basic steps of verifications we need to perform after layout. Next is with the generated PAX netlist, we will do post layout simulation. And if the specs are met, then we will go for IO pad frame design for tapeout process. Or if not met, we will again have to change the layout and do all these things. So it's the iterative process. And then after completing the layout with IO pad frame, we will have to check again DRC check. Then another attachment is required, Siliguri. Siliguri attachment I will be showing in the diagram. Next, verification again check. Again we have to check the layout. Next, GDS2 extraction will be there. So these are the steps for analog design flow. So I have marked with color. One is for front end and this for back end. So up to simulation, schematic entry and simulation, it is termed as front end design, and rest are all back design till chip fabrication. So these are the analog IC design flows chart. Next, in every step, what are the tools we are going to be using? So that schematic and simulation, we will be using Cadence Virtuoso schematic editor and Cadence Spectra tool for multi-mode solution for simulation. And another company, Synopsys custom designer tool, you can also use. C designer command is there. And Synopsys A-Spice tool for simulation we can use. Next, for layout and shielding attachment, we can again use Cadence Virtuoso layout editor. And the design verification, we can use the tool from Cadence, Ashura, or Caliber tool from Mentor Graphics. So I'll be showing you through Caliber tool from Mentor Graphics tool. So these are the tools. Again, same tools will be using post layout simulation. We will be using same tool, IOPad frame design, complete layout with Cadence Virtuoso layout editor. So these are the 6 steps. of doing the chip tapeout through cadence tools or other EDA tools. Next, let's take a design example of a CMOS inverter. One is familiar with it. So these are the two MOSFET based design, and I have shown a schematic design and symbol design and expected output, transient output, and voltage transfer curve. And we know the truth table of NOT gate or inverter is this. This is the very known things I have just shown you for you brush up or memorize things or recalling the things. So we will be doing one design of inverter and we will check the output, both transient and voltage transfer curve we will obtain. So let's go to the demo and in the cadence and see the results. So actually for running the cadence we require one Linux OS because all the tools are installed in Linux. So for running the cadence swiftly, we have to know the Linux command also. So these all tools basically run in Linux platform. Windows very less tools are there that will run in Windows, but most of the tools in EDA or tools category they run in Linux. So I am going to my working directory where I have designed or I have make the project folder to demonstrate. So you have to make one project directory. This is my working directory. So in working directory, some important files we need to check for. First of all, we need to check for cds.lib file. cds.lib file is there or not. It will search for cds.lib file. It will show. Or you can also search like manually, you can check for it because it will take time. I am running through virtual machine. So you can check for whether in this folder cds.lib, this here you can see cds.lib file is present or not. You have to check for. Then one script file is required where the cadence tools are installed or not installed. Every path is written here. And another file is required display.drf file. Display.drf file, if you have to search it, display.drf file is there. This file is required for denoting the color code of particular PDK. Suppose if you are using UMC 180 nanometer, then it has some color coding of metal layers. And if you are using SCL, it will have some different color coding. So this display.drf file is responsible for giving you the information about the color codes. So these are the files, important files required to run the tool. So right click here, open terminal. I will be typing a command virtuoso. This is the cadence virtuoso command. ampersand for getting the process ID. This ID, this ampersand is responsible for giving you the ID. Like Windows Task Manager, you can kill the process using this number. So this is the cadence tool, virtuoso tool. This is called console, cadence console, and this is the library manager where I will be setting you the design profile, how I am going to design. Now let's do the design. So for that, go to file, new, library. So we will be creating one new library of your project. Say SIT demo inverter. Give any name. Now you have to give the reference using which technology node you are going to design. So attach to an existing technology library. SCL 180, TS08, SCL prim. These are the library where from I will be using the MOSFETs. So search for newly created a library, SIT demo inverter, new. By selecting this, again go to file, cell view, inverter. So this is the schematic editor of your design of Cadence. Is giving you the editor to edit your circuit under your project library. So for taking any instance, taking any symbols from library, we will be pressing I, and we will be going to this particular library. Here you can give NMOS underscore 18 means 1.8 volt VDD. NMOS 33 means 3.33 VDD maximum you can give voltage, VDC voltage. So PMOS we require, one PMOS is required. Again press I. So you can see here I am designing the inverter using this PMOS. Just W to do the wiring. Press W to wire the circuit. So these are the input and output, VDD and ground. So let's give the pin. So here you can see here create pin is option is there. So you can give B in as input and BDD, GND. You can give input or input output, whatever you can. And next pin is required for B out. So check and save. I have designed the circuit with pins. Now I will be creating one symbol out of it. So for that, create cell view. From cell view, I will be creating one symbol from this schematic. So you can assign the pin position. So I am giving a ground pin to bottom and press OK. So you can see here the whole circuit is modified with a symbol, with a pin. Now using this editor, you can edit this symbol, delete this. Now using this line, you can draw the inverter symbol. Though it is not mandatory, but
Sir,
hello, yeah,
sir, would you please change the background color because it is not actually visible.
background
The
color. It is
background color is black.
back color. Actually, it's a tool color. I cannot change even because this is
Yes,
tool
yes.
cell. Uh,
No, background color is black. Therefore,
yeah, background color is black. It is by default black. I cannot able to change this because this is tool color, editor color. Uh,
okay, sir, proceed.
okay. Hmm. So just arranging the pins for getting a better look. So check and save. Now you can use this symbol wherever you require. So this now we'll make one other test bench. Test bench where we will test the circuit. Now you go to your library, check the symbol. Next, you take some voltages and grounds so that you can test it. So press I. Now we have to go to analog library. This will be given by Cadence itself, generic library. So here this is maximum 1.8. One is for input and this is for biasing. Or you can use one VDD connections for reference. Actually, I am virtually shorting it using this instance. Now GND ground. Press W. Next, we require a load capacitance cap. I want to call that. So again give pin E out and let me give not BTC DC source. I am giving you transient source so that you can do all the analysis using same sources. E pulse. Well, we have to configure the pulse 0 to 1.8 maximum. Suppose period 10 micro, rise time 10 pico, hold time 10 pico, and pulse width 5 micro, half of the period. So check and save. Now we will start doing simulation to check our circuit. So in this way you can also design amplifier, whatever the process is same, the steps are same, but due to the shortage of time I am showing you the inverter as an example or getting a easy grip. For you it will be an easy one. Let's give a name to the input, where name you can add using this label. You can give one name to this input. Check and save. Now go to launch analog design environment version L, where we will configure the test. So for that we have to go to setup, give the model libraries of SCL, because the NMOS and PMOS are defined in it should be defined somewhere. So the definition file of NMOS and PMOS is given by Foundry itself. So we have to give the Foundry files. So my directory will be SCL, models. And these are the section of the model file. We have to specify the section. This is called typical section. Means Foundry has given all corners of the MOSFET, all the extreme corners where a MOSFET can be operated. Means it may be fast. Means PMOS and NMOS both are fast. Means they are operating in 1.96 volt. Voltage, if voltage is high, then how the MOSFET will operate? Suppose SS corner, so 1.69 voltage. So if voltage get down or some fluctuation is there, the circuit will operate or not. So using this corner, we can check this. So now for optimum, I am using typical simulation for demonstration. Now go to analysis, choose DC analysis. So we will check the DC transfer curve, save DC operating point. Now component parameter, select component, which component parameter you want to vary. So I am selecting this input component, and input component which parameter? DC parameter. I am going to vary the DC parameter. You can also vary all these things, but I am just concentrating on DC voltage variations. Starting from 0 to 1.8, apply. Okay. Now you can see the test is shown here. Now go to output, to be plotted, select on design, input and output. Run. Now the output will come. So as earlier I have shown in the slide, this is called DC transfer curve. Up to 0 to this point, the circuit is taking as 0, and after that it takes from this area, from starting from this, the input is taken as 1. So accordingly the output is switched. 0, the output is high, and from this to this, the output is low. So our DC transfer curve shown perfectly, working the circuit. Now you can check one thing. So you can check this. This is 0.742 millivolt mid value, but you are giving 1.8 volt. So 50% of this 0.9 volt. So if this point, if you want to shift this point to this point, then you will be able to design ideal inverter. 50%, in fact 50% is just transiting. So for that you can use you can open this symbol in new tab. Here you can see the schematic. You can raise the W width of this transistor. So this is gate width and this gate length. As it is a 180 nanometer technology, so effective gate length is 0.18 micro. This unit is 0.18, by default it is in micro. So gate length is 0.18, means 180 nanometer length. Now if you want to change this width, you don't know the exact width, then you give W as a parameter. Apply. Okay. Check and save. Now you go to the window, to this window, and right click here, copy from cell view. So a variable come here, W. Give the initial value 0.42. Okay. So these are not required. Now go to the tools, parametric analysis. You can sweep this parameter W 0.42 micro to 2 micro say, and let's say we are willing to check for 10 graphs. We want to check for 10 points. Now run from this. So it will vary the W and do the simulation for particular W. Some problem is there. Let me check it. Actually, the due to the unit problem, the tool is not able to run this because by default like STL technology node has micrometer, so they are not assigning some unit. So using for this, the problem arises. So I am checking it out. What may be the problem? Scale. Anyway, if you want to simulate this, let me check this simulation directly. There are some wording is there or not. Okay, this is the unique problem of SCL. So I am solving it out. Give a second. So now it will be coming. Now let me run this. Yeah. Now it will be showing some problem again still there. Output is not up to the mark.
Sir, one question
Yeah.
is there in the chat.
Yeah. I will.
Savani ma'am has raised one question that is the tool node specific or we can change the range of the node?
Range of the node. Range of the node means a technology node, or she is answering a question. Technology node you can change by changing the foundry file, because I am showing here for technology node 180 nanometer. So if you want to do it in 65 nanometer technology, you attach 65 nanometer library and do your work. It will
Sir,
show
is
you.
this a GPDK 180 nanometer?
No, this is SCL 180.
First is
SCL 180. So this is the output, but output is not up to the mark because all the output are almost same. It is not changing due to the unit issues of SCL. So it will be solving. I will be showing you some other example using some other node. This analysis, if time permits. But if you vary the width, you will see the shifting of this output. It will be a shifting of output will be shown here. But due to the unit issues, it is not showing here. So that's the problem. So let check with other nodes also. I will be showing you other nodes also, so no problem. But in this way, you can design the ideal inverter by shifting this curve. The curve will shift like this. If you shift the W, you width to the W, the curve will shift like this. You can choose particular W and set the value for ideal inverter design. So this is it for DC analysis. You can save the state also for future analysis. No need to give the model libraries. And so now let's do the transient analysis. Transient for tran, this is tran, and the stop time says 50 micro more than the period. So here you can see this is the transient output. This one, the output is 0, inverted output will be there, and this curve is due to the capacitor. If you want to increase that, if you want to check the rise time, fall time, you can check the values of capacitor. You can change the values of capacitor, and you can simulate it and get the desired rise time, fall time. Suppose if you want to get another rise time, then change the capacitor, again run it. So you see here bend. Previously it was less bend, but now you can see some bending is there at the output. These are the rise time delay due to the capacitor values enlargement and maximizing the capacitor value. So in this way, you can do the transient and DC analysis of this inverter, and you can also find the rise time values. So you can use this output, send to calculator. So one calculator will be there and cadence. So in function, you can check the rise time, wall function. Rise time y value 90% and 80%. Yes, okay. So this is the rise time 568.4 nanosecond. So this is the rise time. You can keep this equation to the ADL this. So if you again simulate it, it will show directly the value. It will show directly the value. Yeah. In the value window, you can find the rise time of this waveform. So in this, you can simulate, you can save this state for future simulation or modification of this design. Now close it. Our front-end design part is over. Now we will be going to back-end design. So go to this schematic. Now from schematic onward, we will do the back-end design. So before starting this back-end design, let me go to the PPT again and see something about layout. So this is the basic CMOS structure in back-end perspective. The NMOS part, we have to make one P substrate. We have to take one P substrate upon which N plus doping, 2 N plus doping for source and gate, and body contact point will be there for biasing the body. But in case of PMOS, upon P substrate we have to create one extra annual, and then P plus 2 regions will be there for source and gate, source and drain, and for body contact annual contact will be there biasing the body. This body biasing is required for avoiding the latch-up condition in the CMOS circuits. So these are the things. In case of NMOS, source and body is not shorted; it is grounded. Whereas in case of PMOS, body should be shorted to the VDD. So that will be showing you in the layout demo how it should be shorted for avoiding the body bias or body effect, or you can say the latch-up condition. So these are the layout, mapping of layout, and this picture. This P substrate is the black one. The black background is our P substrate. In Cadence Virtuoso layout editor, the black one is the P substrate, and this is the body contact, and this is source, and this is drain, and this red one is the gate. Similarly, in case of PMOS, this pink one is the annual, and this is black one is P substrate common, and this is source and this is drain, and red one is the gate, and this is annual tapping. This is I have shown here. So with this analogy, we will proceed for doing the layout. After that, after doing layout, we will do some checks. We will check layout versus schematic and parasitic extraction. These 3 steps will be done through Calibre tool from Mentor Graphics. Calibre tool from Mentor Graphics. So after that, we will do post layout simulation. Post layout simulation will be done for using the parasitic extraction netlist file. We will see how our design differ after doing layout. Next, we will continue for IOPad instantiation. So first of all, let us do the design and check this how it can be done. So again, let's come back to the Cadence. Go to launch, layout. Wait, I have given some variable in the schematic. We have to change it first. Suppose default value I am doing with default value 0.42. Second save. So go to launch, layout Excel, create new, layout view. Okay. So another editor is opened. So this is your layout editor Virtuoso. This black one is your P substrate. Black background is P substrate. Now we have to set the grid size. That is the pitch. This small dot, the difference between these two small dot. SCL has by default 5 nanometer minimum pitch size is 5 nanometer, means this point to this point SCL has told us to keep 5 nanometer spacing. So let us do it first. Go to display, change the grid size. So the grid size is checked. Now go to connectivity, generate all from source. As we are doing schematic driven layout, means semi-custom based layout or semi-custom based design, we are generating our layout from schematic itself, not doing it our own. So no need of IO pins PR boundary. If we do the layout manually each transistor, then that will be called as full custom based design. But in this I am showing you the schematic driven layout, generating the layout from schematic itself. So you see this PMOS and NMOS generated. Now we have to check the layers. So for that, shift F. You can see here this pink one is annual. This source, this is drain. This is source, this is drain, and this is NMOS. Now we will do the wiring. This red one is the polysilicon for gate connection. So let us design this GC. Search for GC. This is the LAN name GC. Control Shift W for wire. GC should be selected here. They are not selected. Now selected. Or you can press R for rectangular drawing. So see here fly lines is there. You can check the fly lines. Join this. Or if you want to avoid polysilicon, because polysilicon induce resistance, so it will generate some resistances. So if you want to avoid this, then you better to use one thing. Press O. Use some via metal 1 to poly. Now use metal 1 M1. Press R or Control Shift W. Join this. Okay. Press S to adjust this layer. Now my gate connection is over. Next, P out. If you want to avoid M1, you can also do it by like this. There is total 4 metal layers are available, so you can use any metal. Press O. M1, M2 layer. VI is there. VI is used for connecting the two different metal. For shorting the two different metal, we use VIA. Now metal 2, as we have given via metal 2, so connect this R, press by pressing R, you can also connect. Okay, so like this you can also draw. Next, this is for ground. And this is for GND, VDD. Sorry. So almost connections are over, but we need one body base, means body tapping. So for that, press I. Body tapping is already done, created. So I'm just tapping this. So I have just connected the body of PMOS with the annual metal one, or sorted the body with BDD. And similarly, press I, P active for NMOS. This is what I have done for body biasing. Save. Okay. So this is the design overall. Now we'll check the DRC errors. If any DRC errors, design rule errors are there or not. So for that, we'll go for Caliber. This is a mental graphics tool which is attached with Cadence. Run NMDRC. So we have to check the runset file, or you have to check the rule files. You go to rule file, you have to check the DRC header file from SCL. They will provide the rule file header file, and output you have to check whether it is okay or not. Then run DRC, overwrite. Now we are doing layout verifications. So these are the steps, 3 steps we will be doing: DRC, LBS, and PEX. So some errors are there. That is DC1, DC2, 6W, 9X, and 11X. 11A the width, M2 width minimum is 0.28. So we will check this. Go to select this highlighter. It will mark the error in the layout. Here the error is. Now press Q and give the width 0.28 as it's given written in the error window. It should be 0.28. So now I'm giving the width of this metal 0.28. Save. Again run DRC. So DC1, DC2, 6W, 9X, and 11X. These are the error for full chip design. When full chip design will be done, this error will be removed. So this is a block level layout. So that's why this error DC1, 6W, this density error and coverage error, we can avoid this. So as of now, the DRC is clean for me. Now we will check for LBS. So for LBS, we have to give the pins. We have to assign the names of the pins. Let me increase this. Okay. Now press L for level. Now create level. BDD. Select the layer. M1 level. M1 level. You can change the font. Next is your GND. You have to check with which metal layer it's connected. If it is M1, then you have to check. You have to take M1 level. If M2, you have to take M2 level. So and beans with same metal. So BDD, place it. Next is GND. Next is bean. Escape. Press escape for cancelling previous command. L. V out is required. So V out. which is metal 2 level. So you have to change the metal 2 because B out is connected with metal 2. So this is the metal 2. Save. So I have given the pin names also and layout is DRC clean. Now we'll go for LBS check. Run nm LBS. So run set file is there, means I have already saved the states, giving the layout file, rule file, everything. So it's okay. Okay. Run LBS. So LBS is correct. Yeah, comparison result correct. Smiley is there. So it's a basically a dream for the designer, layout designer, to see this face after LBS. In case of bigger design, it's lots of time to correct it. If any problem arises, it takes lots of time. So LBS, up to this LBS is clear. No. Next, go to caliber, run PEX, parasitic extraction. Because this metal layer, polysilicon, induced, it will generate some capacitor and resistor. So we have to generate this and simulate the design using this netlist. So check the rule file, header, still is there, output, caliber view should be the output is caliber view. R, C and CC. R, C extraction will be there and C means coupling capacitor or coupling capacitor. This extraction will be done. So here you can change some settings. Schematic, create all terminals, edit, and press OK. So here no warnings, no errors are there. Now close it. You can see here one caliber view is created here after layout. Here you can see this consists of resistor generated from the capacitor, generated from the layout itself, and this is the MOSFET and spins. So using this file we will simulate now. So that will be called your post layout simulation. So again we will go to the inverter TV schematic, go to launch, ADL, load state, as I have saved the previous state, previous output. Now we will change something. We will change Now let me check these values. 568.3 3 nano. So go to environment. We will change this to caliber. Now it will take the caliber view into account and simulate it. Run it. This is the output from layout itself. This is the layout output, and this is the layout of output variations. Time is now decreased due to the generation of some other register capacity bypass circuitry. You can also change again to see the effect. So this is schematic output. Now here you make append, change the environment to caliber again, run it. Rise time is same as schematic. So these are the two outputs. One for layout. This lower one is from layout. Upper one is for from schematic. So you can merge it and see the things.
Dr. Saurabh,
Yes, sir.
Acha, I am quite doubtful the students are taking up all the points that you are discussing. So
Yeah.
I would advise all my dear students, you can make Dr. Saurabh sir to stop and ask question if you have anything before he goes into these and that and so many topics. He's giving you so in-depth knowledge, but if you don't understand all these, then there is no meaning in delivering.
Yes,
So
sir.
I would advise all the students, if you have any question, you can ask. Make sir stop and then proceed the thing. Please.
Okay. So this is the total post layout simulation I have shown here. One from layout, one from schematic I have shown here. Difference you can very minor differences there because only two transistor circuit is there and one capacitor. Some capacitor will be generated due to the parasitics. So it will not be much difference at the output. Will not show any some reasonable difference at the output. In case of large circuit, it will show deviation, or for high frequency circuit, it will show the difference. So now I up to this, if anybody has any doubt, please raise question so that I can check whether you are with in the same page or not. So I think you have no doubt. So let me go to the PPT again. So our task till now, we have done this up to this post simulation I have done using the parasitic extent file. I have shown you the difference between layout and schematic results. Now I have shown you the DRC, LBS and PACs using this caliber tool, and now I will be using some other tools to generate the pad frame. We are now going towards our tapeout process, means chip tapeout process. So for tapeout process, you can do it manually, means placing every IO pads manually in the layout editor, which takes lots of time, even month it can take. And other way is doing automation pad frame generation using Verilog scripting. I hope all of you know the Verilog coding. So using Verilog coding, we can do automation in pad frame design with some other tools called Innovus, Cadence Innovus tool. So next, after generating this IO pad, we require some files for generating the IO pad frame. So one is your Verilog netlist file, another is LEF file of IOPad, layout extraction format file, IO assignment file, and Cadence Innovus tool is required. DDS2 extraction file is required for extracting the DDS file of this IOPad frame, and then importing to the Virtuoso and check DRC, design rule check, as earlier. So these are automated IOPad frame design methodology, or you have to follow this for designing the IOPad using automation or scripting. So overall the chip will look like this. So the green color border is called the seal ring. Seal ring. This seal ring will be used. That will be grounded, and this will be used for the 5G precision saw to cut the chip from the wafer. The chip will be cut. This will be a die. Actually, the total with seal ring it is called a die. So SCL gives 2 mm cross 2 mm die size minimum. We have to make our chip minimum 2 mm cross 2 mm. So up from shielding to shielding, it is 2 mm, 2000 micrometer by 2000 micrometer. And the IOPads, these are IOPads. These are IOPads, and the yellow color that is shown here, that is called the filler cells. That is, you have to fill the gap between this IOPad. It is 2 IOPad. There should not be any gap. So these are filler cells, and under this BDD and ground ring are there. You can see here BDD and ground ring, and inside this you can place the inverter block or whatever block you have designed inside this. You can put this and do the wiring. So another is silicon number. The foundry will give you the number of the IC number. You have to place it here. And so these are the overall structure. Seal ring should be grounded, and we have to make this chip now with your inverter. So let's go to the demo again. We have made our layout. Now let me invoke another tool. I will show you the steps only. It is already done. So this is another folder where I will be using another tool called Innovus. So Innovus is a RTL to GDS or PNR tool, you can say, given by Cadence. Place and route tool. Placement and routing is done for physical design is done in this tool. Innovus implementation systems or Innovus design suite by Cadence. So it will take some time because its software is heavy. So it for running this it requires some files. So these are the files: map file, .map file, LEF file. This is software. LEF file of technology. These are the LEF file layout extraction format file of technology that will be given by your foundry. and this is the GDS extraction file, map file. These are required, and you require one Verilog file, pad frame test. So this is a Verilog code, simple Verilog code, where I have given some input and output pins, and some IOPad name. These are IOPad name PC3 D00. That will be available with every foundry. The particular foundry has particular IOPad name. We have to give that name here, and we have to instantiate it and write the pins accordingly, map the pin accordingly. So this is a simple Verilog code. Only to do the automation, I have just done it. And these are the corner cell of the pad. I will be showing in the demo itself. So you require one Verilog file, netlist file, iopad frame.io assignment file. This is io file. So here we will be write all the IOPad, the placement of the IOPad, where the first IOPad will be placed, whether in bottom or right, left of the chip. We have to assign this. So this is called IO assignment file. And for doing automation, we have to write one tickle file. So this is the tickle command given by the Innovas tool. So I have just written the command only, or you can do it manually graphically here. Without doing scripting, you can do manually here. Go to file, import design. You have to give the Verilog file, Verilog test file, and LEF file you have to give. LEF file you have to give the technology node first, then your IOPad LEF file, then IO assignment file, padframe.io, PowerNet VDD and ground. So like this also you can import the design. So I am not doing like this. I am just running the script. So this script command, whatever I have done in graphically, this command line also do the same thing. I have given the map file here. I have given the Verilog file here, IO assignment file here, BDD and PowerNet is there, and these are the floor plan of the IC. This is the spacing between the IO pad and the power rails. So I will be showing here in the demo itself. Now let me run this. The source padpad.tickle. So it is running now. So see here, the chip frame is ready here. So these are the corner cell, iPad frame corner cell I have told earlier in the Verilog file. It is written here, Verilog corner. These are IOPad files, and these are filler cells, and these are the ring of the VDD and ground ring. Okay. So I have just made the frame here, nothing else in this tool. Otherwise, it will take lots of time if you do manually these things. So press close it, as it has extracted the JS file that will be included in the Virtuoso layout editor. So one GDS padframe.gds file is loaded here, generated here. Now we will create one blank library, new library, SIT pad.
Sir, sorry to disturb you, sir.
Yeah, please.
Sir, actually, these are the students from BTech,
Yeah,
first
yeah.
year, second year, third year.
Yeah, yeah.
So at that moment, it is very difficult to understand, sir. Whatever the last portion that he was
Yeah, that's why
explaining.
I'm not telling you the debug. I'm just showing you the these things. You are just no need to get all the grips. Just see how
Yes,
the things is going on. I am recording the video of this. I will be sharing it through my channel so that they can see repeatedly. That can be a reference to them further.
very good, sir. Few students are there that they want to ask some
Oh,
questions over the
okay, okay.
some.
Please, please.
Other student, how to perform this execution. You don't know anything. How to design a very simple circuit using the software. This is the question. Just ask.
Hello, sir.
Yeah, tell me.
Sir, thank you to give me the chance. And sir, how to design this? Can you tell me about something?
Hello. I am not able to listen.
Sir, tell me something about how to design the chip.
How to design? Hello.
Sir, how
Hello.
to make
I am not audible. You are not audible to me.
Sure.
Yeah.
We will ask a student, like according to him, how to
Hmm.
draw a simple circuit using the software. So you have that opportunity to design in your institute, but we have no opportunity like that. We
Yeah,
have no
yeah,
software like Cadence. So how to
yeah, yeah.
handle this situation? Is there any pirated version of the Cadence software so that we can use?
Yes, yes. I can share the link in the get. There's a link. Crack version is there. I will be sharing the link with you or in the WhatsApp. I have Manoj sir. I will share with Manoj sir.
Yes, 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 sir.
So everything will be loaded, preloaded, just to run it and whatever the steps I have shown here, you can perform this.
Any other question?
I hello? Yeah.
You want to ask what is the future prospect of real estate design? Means if you can design a very simple circuit, can you proceed for a very complex logic circuit that you can design through this software?
Yes, yes. A complex to complex you can design here.
Sure. And what is the goal or opportunity of designing that circuit? Means it is industry standard circuit that we can design through the software.
Yes, this software is you will get the same interface in the industry. No change.
Sure.
This same software tool will be used in the industry.
And so many softwares are there. Like the tools are very I mean, useful, like your Xilinx, like the
Also,
Verilog and T-Spice,
no,
the
no,
Better Graphics.
because I'm telling you the tools actually cadence, maintenance, synopsis. These are all industry standard tool. And Xilinx and Vivado for testing. FPGA burning FPGA, the Xilinx tools are used. Burning using FPGA burning other things. FPGA implementation we can do for using by Xilinx Vivado tools.
Can you design one prototype using the software? Directly you can link any FPGA or CPU in this prototype. Whatever the design that we have developed,
Huh.
can you transfer the design to any security based system or the
Yes, 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 yes. Everything can be. I will be showing you at the last moment. I will show you what will be the outcome. Hello. Yeah. Yeah. Any questions or any more questions?
sir, would you please highlight that portion? How to
Yeah.
transfer my design to any CPLD or the FPGA? I think that will be very interesting, sir.
Yeah. Interesting, but the right now the demo it will take some lots of times to show you the things because
Acha.
yeah. I will try to see you the through FPGA implementation. I will show you some glimpse of this. I will show you at the end of the video or at the end of the work hand session.
Few teachers are
I,
all there through the online mode. So if you have any question, you can ask our research person so that we can communicate with him. Sir, one question is there.
hmm.
Sir, like the free software, there is Xilinx. How is Cadence is different from Xilinx?
Actually, there is two flow. One is FPGA implementation flow, and another is ASIC design flow. Whenever you design ASIC, then you have to follow this cadence synopsis and mental graphics tool. And whenever you want to do FPGA implementations and for checking your code, whether your code is perfectly designed or not, then you go for Xilinx Vivado tools. You will be using Xilinx Vivado tools and dump it in FPGA. It will show you the results.
Okay, sir.
Okay. So ASIC, if whenever you design one ASIC chip, you have to follow this tool, this flow. Whatever I am showing. This is the ASIC design flow, analog ASIC design. And whenever you want to implement a design in FPGA for checking the reliability of the code or validity your code, then you have to go for Xilinx Vivado tool. Okay.
Yes, sir.
Okay. So should I proceed or any questions?
Yes, sir, proceed.
Okay. So now, as of now, we have seen the pad frame, and we want to import the pad frame from Innovas to this tool, that whatever we are using now. So pad frame, one blank library I am creating. So this is one blank library. Now we have to attach this technology library to SCL. Next, go to Virtuoso, File, Import, Stream. So here we have to give this TDS file, whatever generated from the Innovas tool just now, this TDS file. Library is the blank library, whatever you have created now. Pad frame. More options. You give some reference library from which library this IO pad will be shown. IO pad library. SCL library. So this is the reference library. Next, layer map file. Translate. No. So see here, this is the pad frame we have just now designed for IC design. So it's a 16-pin IC and BDD and ground rail. This is BDD and ground rail. So now you can put your design here. press I, and wherever you have designed the inverter layout, you see here it is too small. This is too small in comparison to this size. So you can keep here anywhere and draw the lines. Press R and draw the layers. BDD, suppose here press dia because this is some metal 3 layer is there. So stack using different metal M1 and M3 layer by via. You can place here. Now using M3, you can connect this to VDD, and next one is a ground. So again M3, M3 to top metal because yellow one is the top layer. Increase the via size. So M3, this is for ground line. Now again using metal one, you draw the lines of ground and connect this. You can use via. Place here. Now BDD and ground line I have given. Now input and output. So let me check one pins, which pin can be given. So this is one pin, you can use it. Avoid using metal one, but for sake of convenience, I am showing you using metal one. Let's short and stop there. Press O. Just see the steps. What will be the outcome? For realizing the outcome, just see the steps. So this is metal 3M. Hello?
Excuse me, sir, there is a question.
Yeah, please.
Sir, how to select the metal used here?
How to select metal? So metal selection is very much crucial for layout. So there is four metal. This is a four metal process. One to top metal. There is M1, M2, M3, and top M. So whenever you require large wiring, means long wiring, long track, you have to select top metal layer because top metal layer has less resistivity. Metal 1 has high resistivity. So if you draw using metal 1, so it will impose large resistance in its path. Here I have just shown you due to the this is metal 1. I have shown you only for convenience, nothing else. I will not prefer this metal layer this long metal one layer to draw like this. So we have to select this through this panel M1, M2, whatever available. You can DRW drawing purpose. You can select, and depending upon the track length, you can select the metal order. If you require a long track, then you use top metal, or width of the metal should be high compared to other widths of the metals. Means you have to follow the rho L by A concept. R is equal to rho L by A. Area should be high to reduce the resistance. So in this way, you can choose the metals and do the layout. I think it's clear now.
Yes, sir.
So now I am just using another via to cross this line. Metal 2. Let me use metal 2. Different metal, because different metal will not short the path. So I'm just crossing metal 3 using metal 2, so it will not short the path. With same metal it will short. So this is the point. We will connect it. So this is the B in is connected now. B in is connected. Only B out is left. Suppose this is B out. So you can connect using metal 2. So if you want to draw large track, then you have to increase the width of this metal. Use metal 2, metal 3. Stop there.
Sir, another thing is that, so the
Yes.
design which you created, why is
Hmm.
it that so small? Why don't you zoom it?
Oh
It will
no,
be easier.
because because the IC, the die whatever this is selected frame is 2 mm cross 2 mm. This the layout is too small comparison to the pad frame. That's why it is not been shown here. You can zoom, if you zoom, you can see the design whatever I have done designed earlier. But the pad frame is too much bigger. That's why it's not shown. It's not able to see properly. We are not able to see properly.
Okay.
So that is no problem. You can zoom it and do the wiring. So here you can connect this. So in this way, two pins are required. So I connect. Now VDD and ground I should to connect through a pad. So let me check the VDD and ground. Control F. So here you can see VDD PB0I is my ground pin, ground pad, and PBDI is the VDD pad of SCL. So VDD pad, we have to connect VDD na. So Shift F. So here you can see VDD. So press O. Using top amp, you can also connect top amp, top metal layer. But this is again top amp, it will be shorted. So that's why I'm stopped here. Press O, top amp, and say metal 3. Now using metal 3, I've connected to this pin. So BDD pin is connected now with this cell. Similarly, Control F, again you see the 0I. This is the ground pin. Shift F, BSS is there, you can see. So BSS is the outer ring, no issue. Just using top amp, you can connect this. So this is it. Our inverter chip is ready as of now. Here the blank space will be filled with the dummy layers. There is a separate steps. I will not be showing here. And another thing is shielding attachment is there. And then again dummy filling will be there to fill all the blank spaces, because we cannot keep the blank space in the IC. We have to distribute all the layers uniformly throughout the chip. So in this way, so this is the corner pad. You can see these are corner pads, and these are the fillers. So in this way, you can design your chip. Some other sign of process are there left. So this is that will be complicated for you. So that's why I'm not showing here. So this is the overall chip design. Now you can check the DRC, LVS. LVS cannot be checked. Only DRC is can be checked here. Again DRC. So it will take time because it will check all the pads DRC also. Some DRC error will be there due to the blank space. Due to I not filled the dummy, so that's why dummy layer should be filled to remove all the errors, to clean all the errors. Some error will be there, I think. Yeah, 9B 38% checking is done already. Now it is a DRC with full chip. So this error, this some errors are there that will be cleared during dummy filling. So this is metal 1 to metal 1 spacing. It can be corrected, no issue. Just zoom it. So this is the error showing. So I am just attaching one metal 1 layer.
Sir, another
Yeah.
question is that
Okay.
is there any provision of providing that how much voltage or something is required? Like
No, no. Oh, yes,
if
yes, 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 yes.
maximum
Uh,
voltage, how much we can apply so that the
yeah,
device is
1.8,
not
1.8,
destroyed?
1.8. Maximum voltage is 1.8. For this PDK, 180 nanometer technology, you have to provide 1.8 volt maximum. And another MOSFET is there for high performance MOSFET is there, 3.3 up to 3.3 volt MOSFET is supported by SCL.
So is it like it is scaled in this software or it is
No, no, no. It is by foundry.
directly?
It is by foundry. It is by STL or some other UMC that PDK library file capability.
Oh,
See, software is independent of foundry, because if whenever you attach foundry, foundry obligation will come. Otherwise, software is independent. Well,
oh,
whatever foundry you attach, that will work like that.
okay, sir.
Okay. So, so that spacing is done now. Let me check again DRC. Full chip TRC check takes lots of time. Now see the previous error is corrected. These are the error due to the full chip the dummy filling error. The dummy filling is not done. That's why it's showing some error. Okay. So this is it for chip tape out. Now, now for fabrication, you have to extract the GDS of this file and send it to
Sir,
the, yeah.
the thing is that it is the design is in the software. So how do you send it to some fabrication
That is what I
process?
am, that is what I am just showing you now. Wait, how you have to send this to Foundry for fabrication. Yeah, see the step. Now if this design, if your design is final, then you go to Virtuoso, File, Export Design, Export Stream, Export Stream. Previously we have imported. Now we will export this file.
Sir,
Yeah.
this design is sent to where? I mean,
Foundry. That is the SCL. You are using SCL library, na? Semiconductor laboratory files are you are using 180 nanometer. So we have to send this GDS
yes,
file to that foundry
yes.
for fabrication. Means you have to send the it's Chandigarh. Chandigarh Mall is there. The fabrication laboratory is there. So you have to send this file to them so that they will generate the chip for you. Okay. I think it's clear now. Layer map file we have to give.
Sir,
Yeah.
there was a network issue. We could not
Yeah.
listen to it.
Yeah, actually, after generating this GDS file, .gds file, you have to send this GDS file to the corresponding foundry. Suppose you are using SCL 180 nanometer technology. So you have to send this GDS file to the SCL for fabrication. Okay.
Sir, in that fabrication process, do we have to do something like take the
For
how the machine which is fabricating, how does it understand that this is the design?
That will understand that by through code, because they will see only the mask layout. This layout they will see only geometry. They will identify. This is metal one. This is metal two. These are the identifiers for the machines. Rest rest all are things are unknown to them also.
Then there some input they have to give the person who is operating that.
They will just input this file to the machine directly. The machine will identify all the layers, and correspondingly masking will be done, lithography will be done.
Okay.
Okay. Next, we will translate this. Okay. Now, see here, minimizing this perframe.rds is extracted here. Now, you can see the size. Okay, 3.4 MB, reasonable size, because using pad frame it will come in MB, pad frame information. So this, you have to send this file to the foundry via email. Okay. So this is the process of sending it design to the fabrication. Along with some other checks are there. They will be telling you what are the files they require. You have to send it accordingly. What are the report file, DRC report, LVS report, other files are required. So they will be telling you by that time. We will be sending you one by one. Okay. So this is the process. Now let's go to the PPT first and see if anything left or not. So backend demo I have shown. So this is the recent work that we have done, and this is done using TSMC 65 nanometer technology tape out. These two chips are done using TSMC 65 nanometer technology. Corresponding publications are done. This is the SVM chip, a support vector machine learning algorithm is converted to the Verilog code. Then Verilog code the chip, then chip is realized. So next is our recent work. These are the recent work from STL. This is the chip. The outcome, final outcome is this. We will get some hard copy of this your design. Okay. So this is our first tip that we have got from the Assembly Situation project funded by Ministry of Information Technology, West of India. So this is a pre-amplifier design for brain-machine interface. So these are the four amplifiers. Two are closed loop, two are open loop amplifiers are there. So this size is 2 mm cross 2 mm, and after packaging, the size increased to 4 mm cross 4 mm. So this is a one poly four metal process, means one polysilicon and four metal layers. And our next work is for using for cochlear implant, a pre-amplified design for cochlear implant. So these red color layers you can see here. These are called dummy layers. Dummy layers. We have filled dummy, and this outer ring is called seal ring. So these two steps are remaining, and then we have to check again DRC. Okay. So these are the dummy layers, red color layers. Then thank you. You can see all this process in my channel VLSI Toolbox. I request all of you to subscribe this channel. You will get all the information related tools, what are the steps, design procedure, everything, both digital, analog, FPG implementation, everything is there in this in my channel. Or if you want to have, if you have any query about this, if you want to ask anything, you can directly mail to my this mail ID I have shown here. Okay. So from my side, it's over. And if anything, any questions are there, you can ask me now.
Sir, just take few questions from the audience. If they have that question.
Yeah.
Anusha sir, you have any question? You can. Please.
Sir, what type of design materials do you take for interconnect?
Interconnect.
What is the
Eh,
present technology for designing interconnect materials?
Interconnect materials. Actually, these are the foundry materials we have used. Standard metal, copper metal ladder used actually here. And nowadays in the foundry itself, it's available with copper metal. Other metals are not still in research. We have not come to that interconnect design.
Normally in textbook, we have come across polysilicide. So is
Policy,
polysilicide, polysilicide.
polysilicon, yeah.
Do you find application of polysilicide in the industry for designing purpose?
Polysilicon, no. I practical circuitry. We have used only copper metal as for designing interconnect.
Okay, sir. Okay, sir.
Yeah.
Any other question? LFP? Do you have any question? Sir, would you please highlight few future aspects, future opportunities for the students who want to pursue their higher studies? They can pursue.
You can also use one software called microwave software, which is perpetual license. You can also purchase by institutes for practicing the layout and schematic design.
Sir, if your students are interested to take part to projects, is it possible to, from research
Yeah,
side, if sir a group they're trying to do some project with the
yeah. They can come for internship. They can mail to the HOD and come for internship for 2-3 months and do internship here, summer internship. So to get acquainted with the tools, what are we are using.
because
Okay.
if you sir you have no opportunity to provide them the parent software. You don't
Yeah,
have that.
yeah. Okay. Instead of cadence, you can use microwave software. Is there? Or microwave software is the microwave. One software is there. You can use it.
So this as good as your parents, if any reference sir, they get some favor from their
Reference.
any difference? If anyone is designing by using both the softwares, what will be the
Yeah.
difference?
Yeah, actually, Cadence is industry oriented tools, so you will get a much more realistic result in Cadence. Means you will get less deviation after designing the IC. You will get less deviation in comparison to other tools, available tools.